Guys, today I'm going to show you guys how to represent floating real numbers using binary, which is the only number system understood by computers and its processing unit. So we will use the mantissa and exponent representation to convert representation to convert. But first, let's convert a real whole denary number to binary, which is a fairly easy task. Suppose we want to convert the denary number 14 to binary. At first, let's write the place values, which is 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. So this place values equal to 1, 2, 4, and 8. Then let's fill up the places accordingly. So for the representation of 14, we need a 1 under the place value of 8. So 14 minus 8 equals to 6. So it's greater than 4. So let's place a 1 under 4. 6 minus 4 equals to 2. It is equal to 2. So let's place a 1 under the place value 2. And 2 minus 2 equals to 0. It's less than 1. So let's place a 0 under the place value 1. So the result is the binary for 14 is 1110 using a 4-bit register. So that was the conversion of a real integer denary value to a binary value. So let's move on to floating numbers now. We can represent any floating number in this form. Okay, let's first try floating numbers. Number equals to fraction multiplied by 10 to the power exponent. So let's say we want to write 2.38 into this format. So 2.38 equals to 238 multiplied by 10 to the power minus 2, as we want to move the decimal place from here to here. So that's 2 places before, so it's minus 2. So in this format, the fraction and the exponent can both be negative or positive. So for the sake of computer science, let's replace the word fraction with the word mantissa. So it becomes number equals to mantissa multiplied by 10 to the power exponent. So we must remember that the denary is a base 10 number system, and for binary it is a base 2 number system. So respectively, let's replace 10 with 2. So the result is mantissa multiplied by 2 to the power exponent. So this is basically what mantissa means. So basically mantissa is the whole number by which you multiply a power of 2 to make it a fraction. So let's move on to make this idea more clearer. Moving on, let's convert the number 14.5 to binary. There are a number of ways of doing so. Converting 14 to denary. So the first one is first method. In the first method, we'll first convert 14 to binary. As we have previously seen, we normally use the place values from 2 to the power 0 to 2 to the power 3 for a 4-bit register, but as 14.5 is a real floating point number, we have to increase the place values to 2 to the power minus 1 and so on. So let's take the values for this place values. So they are 1, 2, 4, 8, half and 1/4. So for the representation of 14.5, the binary, as we have previously seen, for 14 is 1110, and 0.5 we can break it down to 14 plus 0.5. So the binary for 0.5 using these place values will be a 1 under the half place value, so that makes it 11101. So let's just write the final result below. It's 11101. Then we have to place a decimal point after the place value of 1. So here the place value of 1 is here, so after it we have to place a decimal point. This is the same with the answer, so let's place a decimal point here. Then we need to calculate the number of places or the number of digits we need to jump to take this decimal point to the beginning of the number. So it's 1, 2, 3 and 4. 1, 2, 3, 4. So we need to jump 4 digits to the left to take this decimal point to the beginning of this number. Now we can write this number in the mantissa form, and as we know we have to jump 4 places to the left. We take that as the exponent of the digit 2, as we have seen in this format. The binary for the number 4 is 248. It's 0100 in a 4-bit register. So a floating point number uses 8 bits for mantissa. Mantissa is 8 bits, and it uses 4 bits for the exponent. The exponent is 4 bits. and both, let's place the place values for the mantissa register and the exponent register. So the mantissa register, it will be like the following: 1 2 3 4 5 6 7 8. So let's place the place values: -1, half, 1 by 4, 1 by 8, 1 by 16, 1 by 32, 1 by 64, and 1 by, and the exponent register will be like the following: it will be of 4 bits: 1 2 3 4. And let's place the place values. The first place value is negative, as this is in the 2's complement format. So what values should we fill in these boxes? We already have found them previously. We just have to place them under the place values. So we have found that the exponent is 4 and the binary for the exponent is 0 1 0 0. So let's place it accordingly. We'll start from the left: 0 1 0 0. And what should we place in the mantissa register? We also have found that previously. We have to place this value in. As we have brought the decimal point to the beginning, we can now write this as 0.111. So let's just put this value in the mantissa register but without the decimal point. So it will be 0.11101, 0.11101. We will always fill the boxes from the left, and for the remaining boxes we'll just put zeros. If we want to check if this calculation, we have to just add up the place values under which they are ones. So let's add them. So the denary number should be half plus 1 by 4th, half plus 1 by 4th plus 1 by 8th plus 1 by 8 plus 1 by 32 multiplied by 2 to the power, as this binary number equals to 4. So it would add up to 29 by 32 multiplied by 2 to the power 4, 14. As our results have matched with the initial number we used to calculate the binary of this floating point number, we now know that our mantissa register and the exponent register. So let's move on to the second method. So let's again take the number 14.5 as the exam. In this method, we will be breaking the number in a form which represents the place values. So we can write 14.5 as 29 by 2 as a proper fraction. We can multiply 29 by 2 by 16 by 16 to make the denominator greater than the numerator. So 29 by 32 multiplied by 16. Then we have to put the numerator numbers, which are powers of 2, to equate to 29. So 16 by 32 plus 8 by 32 plus 4 by 32 plus 1 by 32 multiplied by 2 to the power 4. 2 to the power 4 is equal to 16. So we just replace 16 by 2. Then we have to simplify the numbers in the bracket. So it's 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 32. Then we just have to put them under their respective place values in the Mantissa register. So let's write the place values for the Mantissa register. It's -1, half, 1 by 4th, 1 by 8th, 1 by 16th, and 1 by 32. And let's write the place values for the exponent register, which is -8, 4, 2, 1. Let's draw the boxes. 2, 3, 4, 5. One, two, three, 4. So as we have seen that if we simplify the numbers in the bracket, they become similar numbers to the place values. So we just have to match them to the place values and write ones under the numbers we have in the bracket, in this bracket. So we don't have a -1 here, so we'll just write a 0. We have a half, so we'll write 1. We have a 1/4, we'll write 1. We have a 1/8, we have to write 1. We don't have a 1 by 16, so we'll write 0. We have a 1 by 32, we'll write 1. As for the exponent, we have to convert the exponent or the power of 2 to binary. So if we convert 4 to binary, it's 0, 1, 0, 0. So this is our number in the Mantissa and exponent representation. Both the representations we saw are in their normalized form. We use normalized representation so that we can ensure the maximum accuracy of the number is preserved. So how do you know that they're in their normalized form? For a bit pattern in its normal form, for all positive numbers, 14.5 is a positive number. So for all positive numbers, the Mantissa should start with 0, 1. This is an essential for all positive numbers and which are in their normalized form. And for all negative numbers, the Mantissa register should start with the digits 1 and 0. If our real number is not represented by its normalized form, then there is a risk that a loss of accuracy may result. Another thing we must consider is that we can increase the number of bits in the Mantissa part and hence decrease the number of bits in the exponent part, as the total number of bits is fixed. So we can just adjust the number of bits but cannot add or delete one. So what happens if we increase the number of bits in the Mantissa part? If we increase the number of bits in the Mantissa part, we get more place values. So 1 by 8, 1 by 16, 1 by 32, 1 by 64, 1 by 128, and so on. So as we can see, we can increase the accuracy of the number by increasing the number of bits in the Mantissa part, but this will result in a decrease in widths in the exponent part, which will result in a shorter range of numbers which can be represented by this particular arrangement. And vice versa, if we increase the number of bits in the exponent part, the range increases, but the accuracy decreases. Let's write what will increase and what will decrease if we increase the mantissa part. If we increase the mantissa part, the range, the accuracy increases, but the range decreases. So that was all for today. We learned to represent positive, real floating point numbers, binary numbers in binary. So have a good day.